Module 5, Lecture A, Logistic Regression. By the end of this lecture, you will be able to explain how logistic regression converts engineering features into fault or pass-fail probabilities, implement sigmoid prediction and gradient-based training for logistic regression from scratch, and evaluate classification thresholds using confusion matrix, precision, recall, and F1 score. Probability outputs, sigmoid probability mapping. In logistic regression, sigmoid probability mapping turns a combined score from measurements like vibration or temperature into a value between 0 and 1. This makes the model output easier to interpret as the likelihood of an event, such as a fault or failure. Values near 0 mean low likelihood, values near 1 mean high likelihood, and middle values suggest uncertainty. Sigmoid mapping keeps the direction of the evidence while converting a model score into an easy-to-understand probability. As the combined feature score increases, the predicted probability rises, and as it decreases, the probability falls. This makes logistic regression useful for tasks like pass-fail decisions, fault detection, and maintenance risk, where raw data must be translated into clear estimates of defect or failure likelihood. Sigmoid probability mapping is most sensitive when predictions are uncertain, so small feature changes can shift borderline probabilities noticeably. When the evidence is strong and the probability is already near 0 or 1, new data has only a small effect. This makes sigmoid mapping useful for turning engineering data into smooth, practical probabilities that support both automated decisions and human judgment. Python code. Sigmoid probability mapping. Logistic regression converts evidence into probabilities, often using a sigmoid curve. This makes it useful for engineering risk decisions, and the example illustrates the idea with small synthetic measurements. We import NumPy to handle numerical data efficiently using arrays and mathematical operations. We also import matplotlib's plotting tools so the script can create visualizations, such as a graph of the sigmoid curve. The sigmoid function converts a score into a probability between 0 and 1. Before applying it, the score is clipped between -40 and 40 to avoid numerical instability from extreme values. The function then uses the standard sigmoid transformation, making the result suitable for probability interpretation. We create a set of engineering evidence scores ranging from -8 to 8, then convert those scores into probabilities using the sigmoid function. This transformation maps each raw score to a value between 0 and 1, making the results easier to interpret as risk probabilities. In this way, different levels of evidence can be understood in terms of their associated likelihood of risk. Check that the scores and probabilities have matching shapes, so each score pairs with one probability. Then, confirm there are exactly 161 probabilities, ensuring the data is complete and consistent for later analysis or visualization. 3 inspection cases are labeled safe, borderline, and faulty. Then each is assigned an evidence score. A sigmoid function converts these scores into probabilities, making it easier to interpret how likely each case is to be faulty. The output explains that the sigmoid function converts any score into a probability between 0 and 1. It then reports the probabilities for the safe, borderline, and faulty cases, each rounded to 3 decimal places. Together, these values give a concise interpretation of how likely each case is after applying the sigmoid mapping. A new plot is created to show how scores are converted into probabilities using the sigmoid function. The scores are plotted against their sigmoid-based probabilities, producing a clear curve with the familiar S shape. This visualization helps show how the sigmoid maps low scores to low probabilities and high scores to high probabilities. The engineering cases are added to the plot as scatter points, showing each score with its probability. Each case name is then matched with its score and probability, and a label is placed just beside its point. This makes the graph easier to read by identifying each case directly on the plot. Horizontal and vertical reference lines make the plot easier to interpret. A dashed gray horizontal line marks the probability threshold of 1/2, while a dashed gray vertical line marks a neutral evidence score of 0. Together, these guides show how scores and probabilities compare with key decision points. The plot is titled Sigmoid Probability Mapping to show that it maps evidence scores to fault probabilities. The x-axis represents the combined engineering evidence score, while the y-axis shows the predicted probability of a fault. To finish the visualization, set the vertical axis slightly beyond the 0 to 1 range so the full curve remains visible. Then turn on a subtle semi-transparent grid to make the plot easier to read, and display the completed plot for analysis. This script shows how logistic regression turns evidence scores into fault probabilities using a numerically stable sigmoid function. It maps scores from -8 to 8 into values between 0 and 1, then checks 3 example cases: safe, borderline, and faulty. The resulting probabilities show how lower scores indicate lower risk and higher scores indicate higher risk. A plotted sigmoid curve with decision reference lines helps illustrate how evidence is converted into probabilities for risk decisions. Sigmoid probability mapping. Logistic regression turns engineering measurements such as vibration or temperature into an estimated probability of a fault or failure. It first combines the measurements into a single score, then uses the sigmoid function to scale that score between 0 and 1. This makes it useful for fault detection because it gives a graded risk estimate rather than only a yes or no result. In logistic regression, the sigmoid function turns a feature score into a probability. Very negative scores produce probabilities near 0, suggesting little evidence of a fault, while very positive scores produce probabilities near 1, suggesting strong evidence. Around the midpoint, small score changes can shift the probability noticeably, which makes the model especially useful for identifying borderline cases that may need further inspection. Sigmoid outputs let logistic regression express predictions as probabilities, which makes them more useful for real decisions. The same probability can lead to different actions depending on safety, cost, and context, such as treating a fault risk as urgent in an aircraft part but acceptable in a low-cost product. This probability scale helps engineers prioritize maintenance, inspections, and other actions beyond a simple yes or no prediction. Python code, sigmoid probability mapping. Logistic regression converts scores into probabilities, making it useful for engineering risk decisions. In this example, the idea is applied using simple weld measurements. We start by importing NumPy for efficient numerical work with arrays and calculations. We also import Matplotlib's plotting tools to create graphs and charts. Together, these libraries support both data processing and visualizing results. The sigmoid function converts input scores into probabilities between 0 and 1. To keep the calculation stable, it first limits very large or very small values to a safe range, then applies the sigmoid formula using the exponential function. This prevents numerical problems while producing probability values that are easier to interpret. We create 3 measurement arrays for weld analysis. temperatures from 610 to 730 degrees Celsius, cooling times from 42 down to 26 seconds, and ultrasonic signal values from 0.10 to 0.90. Together, these data support analysis and prediction of possible weld defects. We first compare the lengths of the weld temperature, cooling time, and ultrasonic signal feature arrays to make sure they all contain the same number of elements. An assertion then verifies that the lengths match and raises an error if they do not. This prevents data from becoming misaligned during later processing. The weld temperature, cooling time, and ultrasonic signal are each standardized so they can be compared on a common scale. Temperature is centered using 670 and scaled by 40. Cooling time is centered using 34 and scaled by 8. And the ultrasonic signal is centered using 0.45 and scaled by 0.25. This makes the features contribute more comparably to the logistic score. A logistic model first combines the scaled features by weighting them and adding a constant offset. The sigmoid function then converts this score into a probability between 0 and 1. If the probability is at least 0.5, the item is classified as a defect. The output explains that the sigmoid function converts any score into a probability between 0 and 1. It then displays each case with its score, defect probability, and predicted label. For each case, the label is shown as defect when the class is true and pass otherwise, with the values formatted neatly for easy reading. This visualization shows how logistic regression converts combined feature scores into predicted probabilities using the sigmoid function. A range of scores from -6 to 6 is mapped to probabilities, forming the sigmoid curve. Actual score examples are highlighted in red, and a dashed line at probability 0.5 marks the classification threshold. Labels, a title, a legend, and a grid make the plot easier to interpret. This script shows how logistic regression turns weld measurements into defect probabilities. It standardizes temperature, cooling time, and ultrasonic signal data, combines them into a score, and uses a sigmoid function to estimate the chance of a defect. Each weld is labeled as either defect or pass based on a 0.50 threshold, and the sigmoid curve helps illustrate how the model supports engineering risk decisions. Decision boundary. In logistic regression, the decision boundary is the cutoff that separates one class from another using a probability threshold. The model turns input features into a probability, then assigns a label based on whether that probability is above or below the threshold. In a manufacturing example, vibration and temperature might help predict whether a pump will fail, with the boundary marking the point where fault and normal operation are equally likely. In logistic regression, the decision boundary depends on how the features are represented. With original features, it is a line in 2 dimensions, a plane in 3, or a higher dimensional surface with more features. The predicted probability changes smoothly across this boundary, so cases far from it are more clearly classified, while cases near it are uncertain. This is useful in engineering because it shows how close a situation is to the line between acceptable and risky behavior. A decision boundary is a practical choice, not an absolute truth. Logistic regression provides probabilities, and you choose the cutoff based on the cost of different errors. In high-risk settings like aircraft component screening, you may lower the threshold to catch more possible faults, while in lower-cost inspections, you may choose a balance between accuracy and efficiency. The goal is to make the model's decisions match your operational risks and priorities. Python code. Decision boundary. Logistic regression models smooth probability boundaries for classification. In this pump inspection example, changing the probability threshold shifts the decision boundary and can change which cases are classified into each group. We import NumPy to handle numerical data efficiently with arrays and mathematical operations. We also import Matplotlib's plotting module to create visualizations, which helps us graph data and understand the decision boundaries in a logistic regression model. We create a grid of vibration and temperature values to test the logistic regression model across many feature combinations. Vibration ranges from 0.2 to 2.8, and temperature ranges from 45 to 105, with 80 evenly spaced values for each. These one-dimensional ranges are then expanded into two-dimensional grids, so each grid point represents one vibration and temperature pair. A simple logistic regression model is defined using three coefficients: a bias of -8, a vibration weight of 2.4, and a temperature weight of 0.075. These values control how the input features affect the prediction and determine the model's decision boundary. We estimate the likelihood of a pump fault by first combining the bias with the weighted effects of vibration and temperature to produce a linear score. That score is then passed through the logistic function, which converts it into a probability between 0 and 1. We first confirm that the probability grid and feature grid have the same shape, so each probability matches a vibration and temperature combination. We also check that every probability is between 0 and 1, confirming the logistic regression model is producing valid probability values. Two probability thresholds guide fault detection. A threshold of 0.5 flags faults when the predicted probability is at least 50%, while a lower threshold of 0.3 is more cautious and flags possible faults earlier, even in borderline cases. To find the boundary temperatures for different thresholds, we convert each probability threshold into a logit by taking the natural log of the threshold divided by 1 minus the threshold. This puts the thresholds on the linear scale used by logistic regression. Comparing the standard and cautious threshold logits shows how changing the threshold shifts the decision boundary for classifying pump faults. To find a logistic regression decision boundary, solve for the temperature where the predicted fault probability reaches a chosen threshold. This is done by using the logit of the threshold, adjusting for the bias and vibration contribution, then dividing by the temperature weight. Applying the same process to both the standard and cautious thresholds gives the boundary temperature at each vibration level. The model outputs the probability of a pump fault, and the decision boundary is the point where that probability reaches the chosen threshold. Lowering the threshold makes the model more cautious by flagging more borderline pumps as potential faults. Using interpolation, we find the temperature where the standard and cautious decision boundaries occur at a vibration level of 1.5 inches per second, showing how threshold choice changes the practical fault boundary. A new plotting area is created to show predicted pump fault probabilities across vibration and temperature values. A filled contour plot displays these probabilities as a smooth color gradient using multiple contour levels and a reversed red, yellow, and blue color scale. A color bar is added so the colors can be interpreted as predicted fault probability values. The plot compares two decision boundaries for predicting faults from vibration levels. The standard threshold marks where the fault probability reaches 50%, while the more cautious threshold marks 30%. The x-axis is labeled as vibration measured in inches per second to clarify what the data represents. The plot is prepared to show logistic regression decision boundaries clearly. The y-axis is labeled as operating temperature in degrees Celsius. The title identifies the visualization, and the y-axis range is limited to the relevant temperatures. A legend is added to distinguish the boundaries and thresholds, and the completed plot is displayed for interpretation. This script uses logistic regression to estimate the chance of a pump fault from vibration and temperature readings. It compares two decision thresholds, a standard 50% cutoff and a more cautious 30% cutoff, to show how the chosen threshold changes which cases are flagged. The visualization highlights the fault probability pattern and shows that a lower threshold catches more borderline faults, with example temperature cutoffs at a fixed vibration level to make the model's behavior more concrete. Manual logistic training, sigmoid prediction. In logistic regression, the model first creates a raw score from the input features, weights, and bias. The sigmoid function then converts that score into a value between 0 and 1, making it easier to interpret as a probability. Values near 0 suggest the negative class, while values near 1 suggest the positive class. The sigmoid function turns raw model scores into probabilities for classification. Near the decision boundary, small input changes can noticeably shift the probability, which helps in uncertain cases. At very high or low scores, the output settles close to 1 or 0, showing strong confidence, such as a likely pump fault under extreme readings or normal operation under stable readings. Sigmoid prediction is the forward pass in logistic regression. The model combines each observation's features with learned weights, then applies the sigmoid function to produce a probability. A threshold can turn that probability into a class label. But during training, the probability itself is used to compare against the true label and update the weights. Python code, sigmoid prediction. This example shows how sigmoid prediction can support engineering classification. Using small sensor readings and manually chosen weights, raw model scores are converted into probabilities that indicate the likelihood of a fault. We begin by importing NumPy for efficient numerical work with arrays and matrices. We also import Matplotlib's plotting tools so we can visualize the sigmoid function and prediction results. Store vibration and temperature measurements in a two-dimensional NumPy array, where each row is one measurement set and the two columns hold vibration and temperature. This structure makes the data easy to analyze and manipulate with NumPy array operations. The code first verifies that the features array has the expected shape, 4 rows and 2 columns. This check is important because later calculations depend on that structure. If the dimensions are wrong, it raises an error, so formatting problems are caught before processing continues. We define a simple manual logistic regression model by setting 2 feature weights, 3 and 2, and a bias of -3. The weights control how strongly each feature affects the model, while the bias shifts the decision boundary. These values are used to compute a linear score, which is then converted into a probability with the sigmoid function. This function applies a numerically stable sigmoid transformation by first limiting input scores to the range from -50 to 50. This clipping helps prevent exponential calculations from becoming unstable. It then converts the scores into probabilities between 0 and 1, making raw linear scores easier to interpret. Logistic regression first combines the input features with their weights and adds a bias to produce a raw linear score. The sigmoid function then converts that score into a value between 0 and 1, so it can be interpreted as the probability of a fault occurring. A threshold of 0.5 is used to decide whether each probability indicates a fault. Any probability at or above this threshold is marked as a predicted fault, while lower values are marked as no fault. The result is a set of true or false values representing the fault predictions. The output first confirms the NumPy version for compatibility, then explains that each data row represents higher vibration and temperature levels. It shows the raw weighted scores, converts them to fault probabilities using the sigmoid function, and finally, reports integer fault predictions based on a probability threshold. To plot the sigmoid curve, we first create a set of evenly spaced input values from -6 to 6 using NumPy's linear spacing tool. We then pass these values through the sigmoid function to get output probabilities. This shows how raw scores are converted into predicted fault probabilities across the chosen range. The plot shows how raw linear scores are converted into predicted fault probabilities using a sigmoid curve. It includes the sigmoid line, red points for the machine's observed scores and probabilities, and a dashed horizontal threshold to mark the decision boundary. Clear axis labels, a title, a legend, and a light grid make the visualization easier to interpret. This script shows a simple logistic regression example for predicting machinery faults from vibration and temperature data. It uses manual weights and a bias to turn each data pair into a raw score, then applies a sigmoid function to convert that score into a fault probability. A 50% threshold is used to make a fault or no fault prediction. The output includes the scores, probabilities, predictions, and a visualization of how the sigmoid curve maps scores to decisions. Gradient descent training. Gradient descent helps logistic regression learn by adjusting its weights so predicted probabilities better match actual outcomes. After the sigmoid function turns inputs into probabilities, the model changes the weights to reduce prediction errors. Over time, these updates move the model toward parameters that make more accurate predictions. Gradient descent trains logistic regression by comparing predictions with true labels and using the resulting loss to adjust feature weights. The loss is larger for confident wrong predictions, so the model receives a stronger signal when it makes serious errors. Over time, these weight updates help the model produce more accurate probability estimates. Gradient descent trains a model through repeated passes over the data, gradually adjusting weights so predictions improve. The learning rate controls how large each update is. Too small makes training slow, while too large can overshoot good solutions. By tracking loss and performance on unseen data, we can check that the model is learning useful patterns rather than simply memorizing the training examples. Python code gradient descent training. This section trains a logistic model manually using gradient descent. A tiny engineering dataset keeps the learning process easy to see, while the weights are updated without using machine learning libraries. The script begins by importing two key Python libraries, NumPy for efficient numerical work with arrays and mathematical operations, and Matplotlib's plotting tools for creating visualizations. Together, these libraries prepare the script for data processing and visual display. We set the random seed to 7, so the same random values are produced each time the code runs, making the results reproducible. We also adjust NumPy's display settings to show 3 decimal places and avoid scientific notation, which makes the output easier to read and compare. The data setup uses 2 input features for 8 parts: vibration levels and temperature readings. A separate failure indicator marks each part as either not failed or failed using 0 and 1. Together, these inputs and target values form the basic dataset for a logistic regression model that predicts part failure. The vibration and temperature data are combined into one feature matrix, with each row representing a data point. The failure labels are then reshaped into a column so they align with the features, preparing the data for logistic regression. Before training, we check that the data has the expected structure. The feature matrix should contain 8 data points with 2 features, vibration and temperature, while the target array should contain 8 failure labels. Confirming these shapes helps ensure the data is ready for the training process. To standardize the data, we first find the average and standard deviation of each feature, such as vibration and temperature. Then we subtract each feature's average and divide by its standard deviation, giving each feature a mean of 0 and a standard deviation of 1. This puts all features on a similar scale, which helps gradient descent converge more efficiently and reliably. To prepare data for logistic regression, add a column of 1s to the standardized features. This gives the model a bias term so it can learn an intercept. The resulting combined matrix is then used for training. The sigmoid function converts any real-valued input, often a weighted combination of features, into a value between 0 and 1. It does this by applying an exponential transformation and inverting the result. In logistic regression, this output is interpreted as a probability, which makes the function useful for binary classification. The model begins with all weights set to 0, including an extra weight for the bias term, so every feature starts equally. A learning rate of 0.4 controls the size of each gradient descent update, and training runs for 120 steps. An empty loss history is also prepared to track how performance changes during training. Gradient descent runs for a fixed number of steps, repeatedly improving the model's weights. At each step, the model uses the sigmoid function to turn the current weighted inputs into predicted probabilities, then compares those predictions with the true outcomes to find the errors. It uses these errors to compute an average gradient, which shows how the weights should change to reduce prediction error over time. The model updates its weights by moving them in the direction that reduces error using the learning rate and gradient. Predicted probabilities are clipped slightly above 0 and below 1 to avoid logarithm problems during loss calculation. The logistic loss then measures how closely the predictions match the true labels, and each loss value is saved to track performance over time. The model first uses the sigmoid function to turn the weighted input data into predicted failure probabilities. These probabilities are then converted into failure or non-failure predictions using a cutoff of 1/2. Accuracy is measured by comparing those predictions with the actual outcomes and finding the proportion that are correct. The output summarizes key training results, the NumPy version for compatibility, the starting and final loss to show improvement, the learned weights adjusted during training, and the training accuracy to indicate how well the model performs on the training data. This plot shows how logistic loss changes during manual logistic regression training. A new figure is created. The recorded loss values are drawn as a line across gradient descent steps, and the axes and title clarify what is being measured. A light grid makes the trend easier to read, and displaying the plot lets us visually check whether training is reducing the loss. This script builds logistic regression from scratch using gradient descent on vibration and temperature data. It standardizes the features, adds an intercept term, and uses the sigmoid function to turn linear scores into probabilities. Over repeated training steps, it updates the weights to reduce loss, then reports the starting and final loss, learned weights, and training accuracy. A loss plot shows the model improving as the loss decreases over time. Gradient descent updates. Gradient descent trains logistic regression by using prediction errors to make small updates to feature weights and the intercept. If the model overestimates failure for a machine that passes, it reduces the influence of those signals. If it underestimates failure for a machine that fails, it becomes more sensitive to warning signs. Over time, these adjustments help the model's predictions better match real-world outcomes. During training, the gradient shows how changes to model parameters affect the loss, and the learning rate controls how large each update is. A learning rate that is too small makes training slow, while one that is too large can cause unstable jumps past good solutions. Effective training balances these updates so the model steadily reduces prediction errors. As logistic regression trains, its predictions usually get closer to the labels, so parameter updates become smaller and more precise. Early errors can cause large adjustments, but later updates mainly fine-tune how each feature affects the final probability. Watching the loss helps confirm progress. A smooth decrease suggests effective learning, while stalling or rising loss may mean the training strategy needs adjustment. Python code, gradient descent updates. This example builds logistic training from scratch using a small engineering dataset. It shows how gradient descent adjusts the model weights based on prediction errors. We begin by importing NumPy for efficient numerical work with arrays and calculations, and Matplotlib's plotting tools for creating graphs. Together, these libraries provide the basic tools needed to manipulate data and visualize trends in a gradient descent example. We set NumPy's random seed to 7, so the code produces the same random results each time it runs. This makes the output deterministic, which is useful for teaching and debugging. We create 2 NumPy arrays to store sensor features for the same set of machines: temperature in Celsius and vibration in millimeters. These measurements are used by a logistic regression model to predict whether each machine passes or fails inspection. This creates a NumPy array of inspection labels for the machines. Each label is binary. 0 means the machine passed, and 1 means it failed. These labels let the logistic regression model learn how the input features relate to inspection outcomes. The temperature and vibration features are combined into a 2-column design matrix, with 1 row for each machine and 1 column for each feature. A shape check confirms the matrix has 8 samples and 2 features. This organized format prepares the data for the matrix operations used in logistic regression. To standardize the data, we find the mean and standard deviation of each feature column, then subtract the mean and divide by the standard deviation. This centers each feature around 0 and scales it to have a standard deviation of 1. As a result, features become comparable in scale, which can help gradient descent perform better. The sigmoid function converts a score into a probability by applying a formula based on 1 divided by 1 plus the exponential of the negative score. In logistic regression, it is important because it maps any real number to a value between 0 and 1, making the output suitable for probability prediction. Logistic regression begins with all feature weights set to 0 and the bias also set to 0, giving the model a neutral starting point. A learning rate of 0.35 is then chosen to control the step size during gradient descent, helping balance faster learning with the risk of overshooting the best solution. We start with an empty loss history list to record the loss at each step of gradient descent. Tracking these values lets us see how the loss changes over time and helps show whether the model is learning. The model runs gradient descent for 80 steps. At each step, It uses the current weights and bias to produce raw scores from the standardized features, then applies the sigmoid function to turn those scores into failure probabilities. Finally, it compares those probabilities with the true labels to measure the prediction errors. To update the model, we first find how much the weights and bias contribute to the prediction errors. The weight gradient is based on the average effect of each feature on the error, while the bias gradient is simply the average error across all samples. We then subtract each gradient, scaled by the learning rate, from the current weights and bias to move the model toward lower error. The probabilities are first clipped to keep them away from 0 and 1, which prevents numerical problems when taking logarithms. The logistic loss is then computed by comparing the true labels with the clipped predicted probabilities, giving a measure of how well the model matches the actual outcomes. This loss is saved in the loss history, so performance can be tracked during training. The model uses the sigmoid function to turn each machine's weighted feature score, including the bias, into a probability. Each probability is then converted into a pass or fail prediction using a threshold of 0.5, where values at or above the threshold indicate failure. Accuracy is found by comparing these predictions with the actual outcomes and averaging the correct results. The output summarizes key training results: the NumPy version for reproducibility, the starting and final loss to show improvement, and the learned weights and bias to describe the model's fitted parameters. It also reports training accuracy, giving a quick measure of how well the model predicts on the training data. This plot shows the logistic regression training loss over gradient descent steps. A clear line chart is created with labeled axes, a descriptive title, and a light grid to make the trend easy to read. Displaying the loss history helps us see whether the loss decreases over time, which indicates that the model is improving during training. This script shows how logistic regression can be built manually with gradient descent. It uses standardized temperature and vibration data to predict machine inspection failures, converts model scores into probabilities with a sigmoid function, and updates the weights and bias over repeated training steps. As training progresses, it tracks the logistic loss to show improvement. Afterward, it reports the learned parameters, final loss, training accuracy, and a loss plot summarizing the model's progress. Fault classification metrics. Confusion matrix. A confusion matrix shows how well a classification model performs after its probabilities are turned into positive or negative decisions using a threshold. It compares predictions with actual outcomes and separates them into true positives, true negatives, false positives, and false negatives. This matters because accuracy alone can be misleading, especially when one class is much more common, such as a factory model that passes most parts but misses the few defective ones. A confusion matrix shows how a model's decisions compare with reality. True positives and true negatives are correct decisions, while false positives create unnecessary alarms and false negatives can miss serious faults. Which outcome matters most depends on the setting, such as emphasizing disease detection in medicine or balancing safety risks and false alarms in industry. A confusion matrix helps show how the classification threshold changes a model's predictions. Lowering the threshold catches more true positives but creates more false alarms, while raising it reduces false positives but may miss real cases. By comparing these trade-offs, you can choose a threshold that fits the real-world priority, such as balancing inspection costs with safety risks. Python code. Confusion matrix. Confusion matrices show how a classifier's predictions compare with the true outcomes. Because probabilities must be turned into labels using a threshold, choosing that threshold carefully is especially important when detecting engineering faults. The script begins by importing NumPy for efficient numerical calculations and array handling, along with Matplotlib's plotting module for creating graphs. These imports provide the basic tools needed for later computation and visualization. We store the true inspection results as a NumPy array of zeros and ones. A 0 means the component passed, and a 1 means a fault was found. These labels provide the ground truth used to evaluate the classification model. Predicted fault probabilities from a logistic regression model are stored in a NumPy array with one value for each component. These probabilities are later compared with chosen thresholds to assign predicted labels and evaluate model performance using confusion matrices. Two probability thresholds, 0.5 and 0.3, are used to turn model predictions into binary labels. Comparing these thresholds shows how the choice affects classification results, including true positives, false positives, and related confusion matrix metrics. The confusion counts function evaluates classification results by turning predicted probabilities into binary labels using a chosen threshold. It then counts cases where both the true and predicted labels are 1 as true positives, and cases where both are 0 as true negatives. These counts provide key parts of a confusion matrix for measuring model performance. The function summarizes classification results by counting correct and incorrect predictions at a chosen threshold. It identifies false positives as normal cases predicted as false, and false negatives as faults that were missed. It then returns all 4 outcome counts: true positives, true negatives, false positives, and false negatives. The process checks classification performance across several threshold values. For each threshold, a helper function uses the true labels and predicted probabilities to count true positives, true negatives, false positives, and false negatives. These counts are then printed with the threshold to give a quick comparison of results at each setting. For the first threshold, we use a helper function to compare the true labels with the predicted probabilities and count the true positives, true negatives, false positives, and false negatives. These counts are then arranged into a 2x2 confusion matrix, with correct negatives and false alarms in the first row, and missed positives and correct positives in the second row. Create a small Matplotlib figure in Axis to serve as the plotting area. Then display the confusion matrix as a heat map using the Axis image display function. Applying a blue color map helps make the matrix values easier to compare and interpret visually. Label the confusion matrix axes so the categories are easy to interpret. The x-axis shows predicted outcomes, with predicted pass for non-faults and predicted fault for faults, while the y-axis shows the true outcomes, with true pass and true fault. This makes it clear how predictions align with the actual results. To show counts inside a confusion matrix, loop through each row and column and place the matching matrix value in each cell. The Axis text method is used to center the number horizontally and vertically, making the counts easy to read and the plot easier to interpret. The plot is given a clear title, showing that the confusion matrix uses a threshold of 0.5. A color bar is also added beside the heat map to help interpret the color intensity, with its size and spacing adjusted so it fits cleanly in the layout. Matplotlib is used to finish and display the plot. The tight layout function adjusts spacing so the plot elements fit cleanly without overlapping, and the show function renders the confusion matrix heat map for visual inspection. This script evaluates a classifier by turning predicted probabilities into binary predictions at 2 thresholds, 0.5 and 0.3. For each threshold, it counts true positives, true negatives, false positives, and false negatives to compare performance. It also creates a confusion matrix for the 0.5 threshold and displays it as a labeled heat map, making the classification results easy to interpret visually. Precision. Precision measures how often a model's positive predictions are actually correct. It is especially important when false alarms are costly, because high precision means most flagged items truly need attention. In manufacturing, for example, high precision helps ensure that circuit boards marked as defective are likely to be defective, reducing unnecessary stoppages and costs. Precision depends on the threshold used to turn predicted probabilities into class labels. A lower threshold flags more items as faulty, which can catch more real faults, but may create more false positives and reduce precision. A higher threshold is more selective and can improve precision, but it may miss some actual faults. The best threshold should match the system's priorities, such as avoiding unnecessary shutdowns or detecting as many failures as possible. Precision should be judged in context, not treated as the only measure of model quality. A model can have high precision by making very few positive predictions, yet still miss many real problems, such as early faults in aircraft maintenance. In other settings, like customer support, high precision is especially valuable because false escalations waste expert time. For a fuller evaluation, precision should be considered alongside recall and F-score to understand both accuracy and error types. Python code. Precision. Precision shows how trustworthy fault alarms are by comparing alerts with what actually happened. Changing the alarm threshold affects how many positive predictions are made, so engineers use precision to judge whether alerts reliably match real faults. We begin by importing NumPy, a Python library used for efficient numerical computing. It helps handle arrays and mathematical operations needed for precise calculations in the script. We store the model's predicted fault probabilities in an array, where each value represents the likelihood of a fault for one prediction. These probabilities can then be compared with different thresholds to decide whether a fault is predicted and to evaluate the system's precision. The code uses NumPy to create an array of actual fault labels, where 1 means a fault occurred and 0 means no fault occurred. These labels provide the ground truth needed to compare predictions with real data and measure fault detection precision. The code verifies that the number of predicted probabilities matches the number of actual fault labels. This ensures every prediction can be compared with the correct label, which is necessary for evaluating the model accurately. We use thresholds of 0.5 and 0.7 to decide when a predicted probability should count as a positive fault alert. Comparing these cutoffs shows how the choice of threshold affects the precision of the fault detection system. The code introduces precision for fault alerts by explaining that it compares correct alerts with all alerts generated. This prepares the listener to understand how precision is calculated and what it means. For each threshold, predicted probabilities are converted into fault or no fault predictions. The results are then compared with the actual fault labels to count true positives, where both prediction and reality indicate a fault, and false positives, where a fault is predicted but none occurred. These counts help assess the precision of the fault predictions at different threshold levels. The code measures precision for fault predictions at a given threshold. It counts all predicted faults by combining true positives and false positives, then divides the true positives by that total when possible, using 0 if there are no predicted positives. It then reports the threshold, the positive counts, and the precision rounded to 2 decimal places, helping evaluate how accurately the model predicts faults. The statement explains that higher precision in fault detection reduces unnecessary maintenance alarms. Fewer false alarms make the system more efficient, improving resource use and helping reduce downtime. This script measures how precise fault predictions are at thresholds of 0.5 and 0.7. It compares predicted fault probabilities with actual labels, counts correct and incorrect alerts, and calculates precision as the share of alerts that were truly false. Comparing the two thresholds shows how reliable the alerts are, with higher precision meaning fewer false alarms and less unnecessary maintenance. F-score. The F-score combines precision and recall into one measure, making it useful when both false alarms and missed faults matter. Precision shows how trustworthy positive predictions are, while recall shows how many real positives are found. By balancing the two, the F-score helps reveal whether a classifier is effective overall, rather than strong in one area but weak in the other. The F1 score is useful when precision and recall both matter because it reflects the balance between false positives and false negatives. In predictive maintenance, this helps weigh unnecessary inspections against missed faults that could lead to costly failures. Changing the classification threshold shifts this balance and can change the F1 score. When faults are rare, high accuracy alone can be misleading, since a model may mostly predict the majority class. The F-score is useful when correctly identifying the positive class matters most, such as in defect or fraud detection. It summarizes the balance between precision and recall, but it should be interpreted alongside a confusion matrix because it does not show all error patterns. Depending on the situation, recall or precision may matter more, so the F-score helps choose a threshold that matches real-world priorities. Python code. F-score. The F1 score helps balance false alarms against missed faults by combining precision and recall. Changing the decision threshold affects all three measures. This idea is illustrated using pump inspection probabilities. We import NumPy for efficient numerical calculations with arrays, and Matplotlib's plotting tools to create graphs for visual data analysis. We create a NumPy array to store the true pump fault labels, where 0 means no fault and 1 means a fault. These labels provide the actual outcomes needed to compare against predicted probabilities and evaluate the fault detection model. The logistic regression model outputs pump fault probabilities stored in an array. Each value shows how likely a fault is for one instance, from 0.1 to 0.9. These probabilities can then be used to test how different classification thresholds affect performance. First, confirm that the true labels and predicted probabilities contain the same number of values. This check prevents errors when comparing them element by element. If their shapes do not match, the program stops and signals the inconsistency. We test alarm thresholds of 0.3, 0.5, and 0.7 to decide when predicted probabilities indicate a pump fault. Comparing results at these cutoffs shows how precision, recall, and F1 score change, helping choose the best balance for fault detection. We first create storage for precision, recall, and F1 score results across different thresholds. This lets us compare how each threshold balances false alarms against missed detections, supporting later analysis of the trade-offs between these metrics. For each threshold, the model converts predicted probabilities into binary fault labels by marking probabilities at or above the threshold as 1 and the rest as 0. It then counts true positives where both the actual and predicted labels indicate a fault, and false positives where the prediction indicates a fault but the actual label does not. These counts help compare how different thresholds affect pump fault classification performance. False negatives are counted as actual faults that the model failed to predict. Precision measures how many predicted faults were correct, while recall measures how many actual faults were found. In both calculations, division by zero is handled by returning 0 when the needed positive cases are absent. For each threshold, we compute the F1 score from precision and recall, setting it to 0 if their sum is 0 to avoid division by 0. We then store the current precision, recall, and F1 score so the metrics can be tracked across thresholds. The code prints a header for an output table that compares threshold values with their precision, recall, and F1 scores. This makes the results easier to read and helps show how the metrics change across thresholds. The code pairs each threshold with its precision, recall, and F1 score, then loops through those grouped values. For each threshold, it prints the metrics in a neatly aligned format, making it easy to compare model performance across different threshold settings. To choose the threshold with the best F1 score, find the position of the highest F1 value using NumPy's argmax function. That position identifies the threshold that gives the strongest balance between precision and recall. The code identifies the threshold that gives the highest F1 score and prints it rounded to 2 decimal places. This threshold represents the best balance between precision and recall, helping choose a practical cutoff for the model. A matplotlib figure is created to compare model performance across different thresholds. The plot shows F1 score, precision, and recall as separate lines, each with distinct markers, making it easy to see how these metrics change and relate to one another as the threshold varies. The plot is labeled to show how pump fault classification metrics change across different alarm thresholds. The x-axis represents the fault alarm threshold, while the y-axis shows the metric values for precision, recall, and F1 score. A clear title identifies the plot, and the y-axis range is set from 0 to just above 1, so all metric values are visible. The plot is finalized by adding a subtle grid to make the data easier to compare, along with a legend that identifies each metric, such as F1 score, precision, and recall. The layout is adjusted so all elements fit cleanly without overlap, and the plot is then displayed to examine how fault alarm thresholds relate to classification performance. This script evaluates a logistic regression model for pump fault detection by testing different alarm thresholds. For each threshold, it compares predicted fault probabilities with the true labels and reports precision, recall, and F1 score. It then selects the threshold with the highest F1 score, showing the best balance between catching faults and avoiding false alarms. The plotted results help visualize these trade-offs when choosing practical alarm settings. In this lecture, you learned to explain how logistic regression converts engineering features into fault or pass-fail probabilities, implement sigmoid prediction and gradient-based training for logistic regression from scratch, and evaluate classification thresholds using confusion matrix, precision, recall, and F1 score. In the next lecture, Lecture B, we will go over nearest neighbors. Thank you for your attention. See you all in the next lecture.